Again, feel free to ask questions. Just not use any names. So, let's talk about exam 2. Exam 2 will be Tuesday. I believe that's July 5th. Next Tuesday. Asked earlier, 4 problems. They're going to come from chapters 4 and 5. Not section 5.5. Talk about that today. That's unsteady flow. Talk about it today, but I'm not going to ever put it on exam because it's fundamental differential equations, which I'm not assuming we've had yet. I'm going to show you how we do it. It's not that complicated, but again, it doesn't show up on this exam. Normal resources, it's open book. Mostly for the property tables, but you're welcome to whatever else is in the book. As long as it's these particular authors, any addition's fine. If you want to print material from this book, that's all fine. I think everybody's got a book at this point, so we're okay there. 1 sheet of notes, up to 8.5 by 11 inches. Front and back, not picky what you put on there as long as it's in your handwriting and not photocopied. And again, rules on calculator we've talked about before. If you're not sure, ask me. If I'm not sure about your calculator, I'll give you one of mine. It's been a while since I've had to do that, but I'm not above it. 75 minutes as usual. So again, summertime, if we don't start right at noon, that's not the end of the world. Whatever time we start, I'll give you 75 minutes from that. We'll take a quick break and we'll come back and we'll start chapter 6 after that. So standard rules, I do everything I can to not change the look or the logistics of exams, unless we just have to. Barring anything happening between now and Tuesday, hopefully we don't have to change things. Okay, so we look at topics. Chapter 4 is essentially first law, closed, stationary systems. And that's again, it's always this idea of in minus out equals change. It's a conservation law. A little different way of showing it than a lot of textbooks do, but basically say add all the energies that can come in. Well, if it's a closed system, that's going to be heat and work. So we add the energies that are coming in, subtract the energies that are going out. Again, in a closed system, that's only going to be heat, work. And that equals the energy change. The types of energy that can change are going to be internal, kinetic, and potential. If it's stationary, the kinetic and potential energies do not change. So the only thing changes is the internal energy. And we talked about the process multiple times about how do I find and simplify a first law equation. And we said, well, just draw your system. I'm on the board here on these problems today. Draw your system, draw all the energies crossing the boundary, and that becomes your left-hand side. Add the energies coming in, subtract the energies coming in. Set that equal to the change. If it's a closed stationary system, the change is delta U. Then take it apart, figure out what are your unknowns, right? We talked about generic problem-solving process. So we'll, that's, what are you looking for? What are you looking for? Any problem? That's the first thing. What are we looking for? What tools do you have to find it? If it's an unknown energy, we're probably going to use the first law equation. About the only exception we might run into is if it's a boundary work and if they're only asking for the boundary work and nothing else, and I have enough information with the boundary work definition to find it, and then I wouldn't necessarily have to use the first law. But anything else, any other energy they're looking for, or if it's some other unknown, we saw in the chapter 5 homework, there's one where it's asking for an unknown temperature. Well, we could just use one of the other properties to backtrack and find the unknown temperature. So again, what am I looking for? What tools do I have? Right? What are unknowns, right? And basically, can I solve? Once I've identified my fundamental tools, can I solve it? Do I have as many equations as I have unknown? If the answer is no, go back here. What's the unknown now that I need to find in order to continue? And you can repeat that process until you hit the point where the answer is yes. And then, okay, if you can solve, then solve. So that's simple. It's a very truncated version of any problem-solving process, like the design process, for example. Problem definition, research, brainstorming synthesis, concept evaluation, final design. We're doing the exact same thing. Those of you who've had intro and/or graphics, we talked about the design process. And if you compare that, that's basically what we're doing here. What are we looking for? What information exists? What knowledge exists? What tools do we have to find this? Can we put it together in a format that makes sense? Move forward. If yes, let's move forward. Let's put it together in a format that makes sense. If not, let's go back. Okay, what are now the sub-problems we've identified that we've got to solve? That's just good generic problem solving. Now, and that's, as I mentioned before, that's really our main goal here in this class is to try to make sure we understand good fundamental problem solving. We're going to learn thermodynamics as we go. We're really trying to train you guys to be engineers. So, if my volume changes, for my system, V1 is not V2, then I need to find the boundary work associated with that change. Common practice is we define the boundary work in the out direction. We find it in the out direction, and that means I'm integrating from the initial to the final volume the pressure as it changes with volume. It's the integral of pressure with respect to volume. So again, work is done by a force. In the case of boundary work, what causes or applies that force is going to be pressure, either internal or external, or the difference between the two. And the distance traveled is going to be determined by the volume change. So the work term is caused by a force. We've discussed before if it's compression or expansion, the difference there, right? If it's compression, that is V1 is greater than V2, and I'm going from a larger volume to a small volume, then my boundary work in the out direction will be negative. It's actually work in. We're putting work into the system to cause it to compress. So you can either flip the sign on your integral, which means move and swap these around, or leave it as is, put a negative sign and find the work in, or I leave it as is, and if I get a negative sign, then I make a mental note, okay, it's work in, and then when I plug it into the first law equation, my preference is if I get a negative work out here, I plug it into the work out quantity here, pick up the extra negative sign and cancel out. That's how I was taught. I was taught using traditional signs. This text is a little different on how it approaches signs, but we do have to be aware of, if I get a negative value here, what am I going to do with that? Do I put the absolute value in up here as work in? That's okay. You can do that. Or do I put it in as a negative quantity in a work out term, and negative times the negative makes it positive? Either way is fine. Just understand if it's compression, we're actually putting work into the system. So we just need to make sure that sign takes care of itself somehow. if I've got expansion. Right? And that's what we're basically assuming when we compute the boundary work from initial to final. We're saying it's in the out direction. Here we're saying it's going to a larger volume at state 2 than it was at state 1. Then when I compute the work in the out direction, I will get a positive quantity. So you'll have to wrestle with that and have kind of understand how you want to wrestle with that sign. What I do is again, I just compute it as a boundary workout. I plug that term as a workout term into my first law equation. If it has an extra negative sign, then they just cancel out there. Questions there? Does that make sense? Yeah, make sure work some boundary work problems. Try to work some problems where you need both the first law and the boundary work. So you kind of get used to what do I do? How do I interpret that sign? Right, and those are the fundamental things with chapter 4. We did talk about specific heats, but I want to go ahead and talk about first law for control volumes before we talk about specific heats. So if we talk about first law for what we call steady flow. A lot of texts will call that steady state. Scientists might call it equilibrium, but there's steady flow control volumes. So if I've got a control volume, well, I still can have heat and work, and these are rates. We're going to deal with rate form here. When we're dealing with the control volume, we'll deal with the rate form. So we're putting dots above these rates. So the rate of heat in plus the rate of work in, that's the power input. Right? And we use the term power to refer to a work rate. Minus Q dot out minus the power output. And then I've got the energy of, because it's control volume, I've got the energy of the mass in. Well, I'm going to do a summation. Let's do a general form here. Let's say summation across all of the inlets. M dot times H plus V squared over 2. And I'm not going to include the potential term because, as we've seen, we normally just neglect it. There is a potential energy here, but it's very rare we even consider it. It's nothing I would test you on. But, I wouldn't put a control volume on an exam where there's a huge potential energy difference. It's just not practical for most situations. But you can have an enthalpy change and you can have a kinetic energy change. And we're also going to have those across all of the outlets. So again, summation all of the outlets, M dot times H plus V squared over 2, the enthalpy and the kinetic energy. And that's equal to the change. Well, if it's a steady flow control volume, the change, the right-hand side, is it's actually, again, we're saying the total rate of energy in minus the total rate of energy out is equal to dE for my system, change the energy of my system with respect to time. And what we're doing is we're saying this change is 0 for steady flow. And we've also said that for one inlet, call it one outlet, we'll call him 2. So if I apply, so this is always true, but if I apply a further simplification, so one more assumption to further simplify this, well, something happens with the conservation of mass. I've got one inlet and one outlet. Okay? So conservation of mass always says that the sum across all the inlets of M dot minus the sum across all the outlets of M dot is equal to the change in the mass for my system with respect to time. Just like the first law, in minus out equals change, or rate in minus rate out equals rate of change. Well, if it's steady flow, this goes to 0. If I've only got one inlet, that's 1, we'll say that's m dot 1. Minus the outlet, that's m dot 2, and that's equal to 0. So this simplifies down to m dot 1 equals m dot 2, and we don't even need to differentiate. We just call that m dot. So if it's one inlet, one outlet, we'll use a common m dot for that. Like it just look like it's getting a little out. So how does that help us up here? Well, again, I'm not dealing with multiple inlets and multiple outlets if I can make this assumption. So then I can group these together. I can kind of simplify that just a little bit. I could still potentially have Q dot in or power input. I could still have both of those going out, Q dot out minus the power output, the W dot out. Those all still apply. But again, instead of summations here, let's just factor out the common m dot for both the in and the out, and then multiply by the enthalpy change, H1 minus H2, again, it's in minus out, plus the kinetic energy, V1 squared minus V2 squared, again, that's in minus out, divided by 2, and that sum will equal 0. Now, a lot of times, if you're looking on, if you're looking at solutions manuals, if you're looking at a service like Chag or something like that, they'll just go ahead and move this term over the other right hand side of the equation. And so students will ask me, why is it not 2 minus 1? Well, it depends on which side of the equation it is. Okay. On the left-hand side, we're adding the ends and we're subtracting the ends. So that's the reason on the left-hand side, it's 1 minus 2. What you do after this point to simplify it, that's fine. Now, if you move it to the right-hand side of the equation, it becomes 2 minus 1. It's important we understand why that's the case. When we look back at first law for closed systems, this is the change for the system. The right-hand side is always, when we're first setting the law up, the right-hand side is always the change. This is the change for my system. Back over here on this one, so that the the kinetic energy and the potential energy for my system is right here on the right-hand side. And what we're doing is we're saying, well, if I've got a turbine or a nozzle or a compressor, the internal energy, the kinetic energy, and the potential energy of that nozzle or compressor, whatever it may be, those are not changing as time changes. So the change for the entire system goes to 0. And then what I'm looking at down here is this is just simply the change for the mass as it comes in and goes to the out. So they look the same, right? This looks the same as this. They're not. This is for the entire system in a closed system. This is the difference between the mass in and the mass out. Why am I using H's here? Because it's flowing. Anytime the mass is flowing, we're going to use H's. If it's not flowing, like in the case of this, where this is just the stuff inside the system, I'm using U's in that case. And since this is flowing, I've got the U plus the PV, the pressure required to push the fluid and make it flow. All right, let's see what else. We did say that on the previous exam, we talked substantially about property tables and finding U and H values for water in R134 and the property tables. Here we said, well, if I don't have water R134, I might also need to employ specific heats. So specific heats, we talked about 3 ways we can find changes in internal energy or changes in enthalpy. One being the property tables, great for water in R134. If it's an ideal gas, I can use property tables to find U's and H's if I know the temperatures. For solids and liquids, we'll use specific heats. We can also use specific heats for ideal gases. And basically, for our purposes, is anytime phase is constant, we can use specific heat. Again, we can utilize specific heats if the phase changes, the analysis gets a little more complicated, and we're just not going to mess with it in this class. So I'm not saying you can't use specific heats if your phase is not constant. I'm just telling you we're not going to in this class. All right. So when is that going to occur? When is the phase going to be constant? Well, common scenario is going to be ideal gases. That's normally when we're going to use specific heats. It's going to be for ideal gases. So if I'm dealing with an ideal gas, a change in internal energy is going to equal the integral from T1 to T2 of the specific heat C sub V with respect to temperature. And again, these specific heats for an ideal gas are basically third order polynomials, or at least we've got third order polynomials that describe this behavior with respect to temperature very well. The constant term is easily the biggest and most prevalent within that third order polynomial. So what we normally do is we say, well, yes, it changes, but it really doesn't change much. I can normally assume that that specific heat is reasonably constant. Use the average temperature to get the best guess at what that constant should be. And that will serve as my C sub B average. So basically, I'm assuming that this is a constant. Therefore, it comes out of the integral. Then I'm just integrating dt. Well, that's just delta t. So it's normally a perfectly valid assumption. Just get a good C sub V value at my average temperature, multiply by the change in temperature. That'll give me a really good approximation for delta U. Again, if I know both temperatures, I can go look up U values in tables, or this also works. Same thing with H's. If I need to know H's, like in the case of a control volume, again, that is equal to the integral from T1 to T2 of C sub P dt. But what I normally do is I don't integrate it. I'm just going to go find C sub P at the average temperature, multiply by the change in temperature, and that'll give me a very good estimation of delta P. If I'm dealing with a solid staying a solid, or if I'm dealing with a liquid that I know is staying a liquid, then I can find delta U simply based off the same idea up here. Now, your text likes to use a C sub P. Most texts like to use just simply a C value for solids and liquids. It's the specific heat. Your text likes to call it C sub P. Okay. And again, multiply by change in temperature. If you need the enthalpy change for a flowing liquid, we can mess with that. But I'm not going to give you a liquid staying a liquid where the pressure changes. Okay? This would be just fine. Okay. All right. So what else? Questions for me so far? All right. So 2 chapters, 4 questions. You can probably guess how those are going to get broken up. It's not going to be complicated. But do expect a boundary work problem of some kind. So we probably expect a couple problems from chapter 4 and a couple problems from chapter 5. We talked about, we did talk about in a control volume, it's not always obvious whether I need to worry about the kinetic energy change or not. We talked about how do we know that? How do we know if we need to worry about a kinetic energy change? Well, if it's a nozzle or diffuser, you have to worry about kinetic energy change. It's their purpose. The purpose of those devices is to change the kinetic energy. If it's a turbine or compressor or any other generic control volume, we said, all right, well, can you find the specific? Can you find the speeds? Right? Can you find the speeds? Is it asking for the speed change? Or are the speeds given to you? The answer to all 3 of those are no. Then you're probably just going to neglect that kinetic energy. But if you make that assumption, like I noticed in one of the homework problems, you need to neglect the heat transfer in order to solve it. Make sure you put that down as assumption. Same thing with kinetic energy. If you're just not going to worry about the kinetic energy, just write that down as an assumption. And that way, because inevitably at some point you'll make an assumption that's not correct. And at least if you've written it down in your assumptions and made it clear, hey, I'm simplifying this because I'm assuming kinetic energy is negligible, or V1 is equal to V2 is a simple way to write that. If you put that in your assumptions, then if it's not actually correct, then I know you didn't just copy some equation that know how it worked. You made a conscious choice to use that version of the equation. All right, guys, that I think is pretty good for exam 2 review. So we'll stop there. We'll take a break. We'll come back about 10 minutes. And let's look at. We'll finish out chapter 5.